This module will qualitatively describe the El Niño-Southern Oscillation, or ENSO, and a related phenomenon over the Indian Ocean. Teleconnections associated with these phenomena are discussed in a different module. Taking a look at a typical boreal summertime SST distribution, we notice a quote-unquote cold tongue of SST at the equator off the western coast of South America. It is a northern extent of cool SSTs along an equatorward cold water near surface current where stratocumulus cloud is present beneath a sharp inversion. Notice also how this is an example of how ocean currents transport energy from the equator to the pole in the net, just like circulations in the atmosphere. As a result of these ocean currents, a pressure gradient is present along the equator from east to west. Physically, this is the driver of the easterly flow across the Pacific. The easterly flow reinforces the ocean currents and helps to advect surface ocean water toward the west at the equator. This also induces upwelling off the western coasts of South America and equatorial Africa, especially south of the equator, transporting nutrient-rich water from deeper in the ocean upward and supporting vibrant marine ecosystems. When the temperature of the ocean water at the equator warms or cools relative to its climatological average, this upwelling is either enhanced or reduced. As the temperature gradient across the Pacific increases, so does the pressure gradient, and then so does the circulation. This variability, which usually occurs on irregular interannual timescales, is known as the El Niño-Southern Oscillation. An example of a weak La Niña event is shown here for the same time period as for the SST shown in the previous figure. Shown here are the anomalies of SST relative to the seasonal climatological average over a 40-year-long historical period. Notice how a tongue of cooler than normal SSTs is present near the equator in the eastern Pacific. At the same time, warmer than normal SSTs are present over the western Pacific near the maritime continent. Together, these enhance the cross-Pacific pressure gradient, which strengthens the Walker circulation. Again, this is an example of a weak La Niña case, and we'll see El Niño soon, where the temperature anomalies are flipped. We can visualize this process in a nicer looking graphic from Australia's Bureau of Meteorology. The current figure illustrates typical ENSO neutral conditions. The expected cross-Pacific SST gradient is seen, with cool temperatures in the East Pacific and warm SSTs in the Western Pacific. The gray lines indicate the Walker circulation, with convection occurring in the upward branch over the maritime continent. In the ocean, the thermocline is deeper over the West Pacific, and upwelling is persistent in the East Pacific, where the thermocline is not as deep. During La Niña, this pattern is amplified. More rain occurs than normal over the maritime continent, low-level easterlies are stronger across the Pacific, and the upwelling in the East Pacific is enhanced, while the thermocline is located closer to the surface there. During El Niño, the opposite happens. SSTs are warmer than normal in the East Pacific and cooler than normal in the West Pacific. While the West Pacific is usually warmer in absolute terms, a weakening of the easterly trade winds occurs nonetheless. The depth of the thermocline becomes more uniform with longitude, and upwelling is reduced in the East Pacific, resulting in an anomalous westerly current in the surface ocean and reduced upwelling in the East Pacific, which has important negative impacts on fisheries there as well. The Walker circulation therefore weakens because the cross-Pacific pressure gradient has weakened, and in the cases of strong El Niño events, it can lose its familiar form of driving easterlies across the entire Pacific. More convection than normal occurs over the central and the East Pacific, while rainfall is reduced over the maritime continent and the West Pacific. This can also be seen in anomalies of outgoing long-wave radiation, in which positive anomalies will be detected where the rainfall is suppressed. Now note that this doesn't mean that there's no rainfall over the maritime continent, just less than normal. As we'll see in another module, where latent heating occurs in the tropics has dramatic implications on mid-latitude weather. And indeed, ENSO is known to be responsible for changes in weather patterns throughout the world. The SST anomalies during the very strong 1997 El Niño event are shown here. The deep red colors over the equatorial East Pacific denote SST anomalies of up to 5 degrees Celsius, which is an unusually large anomaly. The La Niña event that followed in 1998 also had large temperature anomalies, about 2 to 3 degrees C in the East Pacific. Note how in both figures, the temperature anomaly, in this example, extends far into the Central Pacific and even into the Western Pacific. This is an example of a particularly strong event. Indices used for operational and historical purposes quantify the strength of an El Niño or La Niña event based on the SST anomaly somewhere in the East or Central Pacific. Different indices consider the temperature anomaly in different longitude bands across the equatorial Pacific. The Niño 3.4 region, highlighted by the bold box in this panel at left, correlates well with changes in weather patterns over North America, so is often used as a proxy for describing the ENSO state. A snapshot of time series of some Niño indices is shown at right for 2018 into 2019. This example shows weak temperature anomalies in the East Pacific in the Niño 1+2 region, and anomalies of generally less than 1 degree in the 3.4 region. These are indicative of a marginal to weak El Niño event. Some other examples of ENSO indices can be found at the link on the slide right here. A similar phenomenon occurs over the Indian Ocean and is known as the Indian Ocean Dipole, or IOD. It involves interannual variability in the strength of the Walker cell over the Indian Ocean and the magnitude of westerlies in the lower atmosphere. As seen previously, during neutral states, convection occurs predominantly over the maritime continent, and in the Indian Ocean, the SSTs are relatively uniform across the equatorial Indian Ocean from west to east, although perhaps a little cooler in the western part of the basin, which isn't really denoted in this figure. During the negative IOD phase, this circulation is enhanced with warmer SSTs over the maritime continent and cooler SSTs near Africa. This results in enhanced ocean upwelling near Africa, just as in the case of South America during La Niña. During the positive phase, the circulation is weakened, with anomalous easterlies in the lower atmosphere and upper ocean, increasing upwelling or reducing downwelling over the maritime continent region, and causing a reduction of rainfall near the maritime continent in Australia. The IOD is usually linked closely to ENSO variability, with a positive phase being consistent with El Niño and suppressed convection over the maritime continent. However, it does appear likely that the IOD is a dynamically separate event, with variability driven by factors other than ENSO. The strong IOD event that occurred in 2019 in the absence of a strong ENSO event is one example of this, and we can see this here, where the reds indicate positive temperature anomalies and the blues indicate negative temperature anomalies, and these are generally on the order of a few degrees C. This is consistent with the positive phase of the IOD that we just showed you, and a reduction in precipitation over the maritime continent. When quantifying the IOD based on the difference in temperature anomaly between the western and eastern Indian Ocean, the 2019 event was one of the strongest in recent history, as can be seen in the time series of the monthly dipole mode index, or DMI, seen at top right, and provides further evidence that the IOD can develop in the absence of ENSO forcing.